plus by stress Z divided by what? By 2. Okay, so this is a stress average that we're trying to find out. Okay, so this is our stress average. Now we are just going to focus on the big circle. Okay, we are just going to focus on XY plane. Okay, so I'm going to deliberately delete these two because we're not going to use them. Because we found them to be what? Not necessary, yes or no? So all these are not necessary. So you don't need to do that. I'll post all these notes, so don't worry. Okay, so we don't need all this. Okay, we need that circle. Okay, so we know how to calculate our stress average. Now, we know that stress Z, okay, we understand that stress Z over here is equal to 0. So this is equal to stress X divided by 2, right? And this is also equal to stress M over 2. And this is my equation number 1. So what do we mean by stress M? Okay, where stress M is a stress, okay, stress induced by the bending moment okay, by the bending moment, and when the shaft, okay, when the shaft is not under any axial loading. Okay, so we are going to assume over here, we are going to assume that Px is equal to what? 0. Okay, there is no stresses in the axial, there's no axial loading. And which is true. When you look at a shaft design, when I say shaft design is basically, hold on, I have a figure over here. Okay. This is a transmission shaft where you have different what gearing systems. You guys did gear design in what? 2DO3, am I right? Right? So you guys calculate what? You are able to calculate the torque, right? You are able to calculate the number of gear teeth, yes? But you did not calculate the stresses on the shaft, am I right? Can you remember for 2D? Okay. Why? Because you need knowledge like this to go into what? Transmission shaft. And if you look at a transmission shaft like this, right, there is no what? Axial loading at all. Most of the time, not all the time, most of the time, we don't have what? Axial loading. Okay, I know there's 2 students out there say, yeah, we are seeing that now, right? Right? There's no axial loading. Okay, so this set of equation that I've written down has no axial loading abilities. Okay, remember that. If I were to give you a problem that's axial load, you cannot use these equations anymore. Clear? Okay. Now coming back to here now. Okay. So from here, we want to calculate the radius of the circle. Okay, so we want to calculate the radius of circle, which is equal to your tau max, right? So the radius of the circle basically is, this is the radius. Okay, R is the radius of the circle. So we are going to calculate it. So tau max is equal to stress average squared, right? Plus by the shear xz squared. Okay, and then that is our equation number 2. Okay, so it is important, right? That it's important to know the tau max of material from mechanical testing. Okay, or you can get from where? Material handbook. Okay. So now, why tau max? Right? Why is it important that we have to what? Use tau max. Okay, so the next equation is y tau max. Okay, y tau max. So if we were to look into a shaft, right? If we are going to do a shaft, okay, or mechanical I cannot spell today, man. Mechanical property of a material. Okay, under uniaxial test. Okay, uniaxial test is always carried out, like those of you that have done 3CO3. Why is that? Because it's cheap, it is most convenient to do. Okay, so now we have a shaft now. Okay, we put it under what? Okay, we put it under tensile loading. Okay, so then we have our element down here, right? Then I sketch our element. Our element only have one direction. So I will call this our x, I'll call this our y, so this is our stress x. Okay. So now if we were to construct Mohr circle, okay, now this is under mechanical testing. Okay. When we construct Mohr circle, how does this look like? It looks like this. So this is our normal stress. Okay. And this is our shearing stress. Element rotate clockwise, element rotate anti-clockwise, and this is our stress x value. Okay, this over here is our stress x value. So for argument's sake, our stress x value, so for example, arbitrary number, this is 500 megapascal. Okay, just an example. Okay, you test this out, you find a yield at 500 megapascal. Then when we start to construct Mohr circle, right, this is what we get. So because this is our point x, this is our point y, and if you want to do this in 3D Mohr circle, this is also our point what? Z. Yes or no? Right? So now, I'm going to draw a line now. This value over here is our tau max. Right? And the tau max will be equal to 500 divided by 2. Why 500? Because the distance from here to here right is 500, right? To find the radius, right? This is our radius, is equal to 500 divided by 2. Okay, right? It's 500 divided by 2. So when that's the case, right, which is bigger? The normal stress value is bigger or the shearing stress? Or which is a smaller value? Is the what? The shearing stress, yes or no? So therefore, we know that tau max is equal to the principal stress max, divided by what? 2, or it can be due to stress yield, divided by 2. Okay? So I'm introducing you to a new criteria now. So the above expression is known as Fresca Criteria. Okay. Now, as I said, my memory is as bad as anything. Okay. So how do we remember Tresca is shearing stress? Right? How do we know? So what I tend to do is I tend to do this. You can laugh at it, okay? This is how I write Tresca. So if you look at the T, I replace as a what? Tau. And the tau is also known as a what? Right? So that's how I spell Tresca, because I can't remember. Okay? So that's Tresca criteria. So this is the reason why we have to calculate what? We have to determine what? Our tau max for what? Shaft design. This is why we have to determine our tau max. Okay? Now, I've just shown you why tau max, because the tau max value is smaller than the yield. Okay? So tau max, no, I think I better zoom out because you guys are having a headache. I'm also having a headache, okay, moving too much, too excited. So we know now that tau max will have a lower magnitude. Okay. So therefore, the design is based on allowable maximum shear stress for ductile material. I have to elaborate down here, is for only what? Ductile material. Okay, if brittle material is like concrete, okay, ceramic, right? This equation will not stand at all. Okay, so only work for ductile material. Sorry, it will only work for ductile material, but not for brittle material. Okay, so we have an expression, right? We have an expression that tau max is equal to stress average squared plus by the shear Zx squared. Okay. So this is our equation 2. Okay. Now we are going to substitute equation 1 into equation what? Number 2. Okay, so now the expression will look like tau max is equal to square root of the stress induced by bending moment, okay, squared plus by the shear xz squared. Okay, so this is our equation number 3. Okay, I'm going to stop here now. Okay, I still have another like 5 equations to solve. Then we can do our shaft design. Okay, I'll see you guys next week.
Eugene, do you know when you're going to post the who needs to do corrections?